As an application of uniform circular motion, I want to look at case of uniform circular motion where the force that's causing the motion is gravity. And this is the example of a geosynchronous orbit. It's also known upon context as the Clarke orbit, after Arthur C. Clarke, the science fiction writer, or Patochnik orbit. So we're going to go through, page and a half of algebra. If you had done this at the right time in history, this could have been known as the Smith orbit, or the Thomas orbit, or whatever your last name happens to be. So the idea of a geosynchronous orbit, I want to put a satellite in orbit some distance above the Earth so that the period of the satellite following its orbital path equals the period for the Earth rotating on its axis. This is quite convenient because then if you point a satellite dish somewhere along the equator and you get a signal, you will always get a signal because the satellite will always be just as much overhead from that radio dish as it is the first time you set it up. So it eliminates the need for tracking and makes satellite communications much, much simpler. So if you do have like a satellite TV that's vaguely pointed towards the south, it is pointed to one of the geostationary or geosynchronous satellites that is beaming out a signal to your happy little radio dish and everybody else's. Okay, a trick in this derivation I'm going to go through is that I don't actually know what the orbital speed is because I don't know what the orbital radius is. But those two are obviously related. The orbital speed means I'm going to go through the circumference of this orbit every 24 hours because I want to match the rotational speed of the Earth. So one thing that I'm going to need to know going forward is how many seconds we have in a day. So I'm going to just go ahead and calculate that quick. A day is 24 hours, so sometimes it feels longer. Thanks to our sexagesimal system of counting, there are 60 minutes in an hour, and there are 60 seconds in 1 minute. So get all the cancellations that I need. 8.64 times 10 to the 4th seconds in a day. So that's a number I'm going to need in a little bit. I also want to make clear that that unknown speed, whatever it is, means that I go through the circumference of my orbit, which is 2 pi r, in the period of the orbit. And that's going to have to be 2 pi r upon 8.64 times 10 to the 4th seconds. All right, for my satellite in orbit, there's only one force acting on it, and that's gravity. So we can go ahead and write out Newton's second law. The net force is going to be inertial mass of my satellite times its radial acceleration. We know for uniform circular motion, the radial acceleration, put in the wrong place, is v squared over the radius of curvature, and the force that's causing the orbit is gravity. So I have big G, universal constant of gravitation, times the mass of the Earth, times the mass of my satellite, over r squared, inverse square law, for the force of gravity. So r here, just to be clear, is the distance from the orbit to the center of the Earth. If I look at just that part, I can simplify things a little bit. mv squared over r is g, mass of the Earth, mass of the satellite, over r squared. And it does not matter what the mass of the satellite is, it's on both sides, so it cancels out. And let me substitute in my relationship for the speed. So on the left hand side, I'm going to have a 2 pi r over the period, quantity squared, and there's a 1 over r. It's going to equal g, mass of the Earth, over r squared. Okay, I clean that up a little bit. That's going to give me 4 pi squared r over the period squared is equal to g, mass of the Earth, over r squared. So I'm going to get r on one side and everything else on the other side. It's going to give me r cubed. So yes, there is a cube root in your future. So r cubed, on this side I'll have big G, mass of the Earth, period squared, over 4 pi squared. And then evaluating that, I want to take the third root both sides. When I do that, we put in values. I have r. Put the radical in here in a second. I'm going to have a big G, 6.67 times 10 to the minus 11, and its units are Newton meter squared per kilogram squared. Earth has a mass of 5.97 times 10 to the 24th kilograms. Period 8.64 times 10 to the 4th seconds squared. Oops. And that's all going to be divided by a 4 and a pi squared. And I need to take the third root of all of that, like so. All right. When I do that, I get r is to be the third root of 7.53 times 10 to the 22 Newton meter squared over kilogram. I have a second squared. Doing that, a Newton is a kilogram meter per second squared. So I'm going to wind up with this being meters cubed. So taking the cube root, it's going to give me 4.2 times 10 to the 7th meters. So 42,000 kilometers above the center of the Earth is where you'll find the geostationary orbit for our planet.